Welcome to this lecture on Aves classification. Have you ever looked up at the sky and wondered how scientists make sense of the thousands of different birds flying above us? Today, we are going to explore exactly that. We will learn how birds are grouped, why this matters for our world, and even look at the physics that dictates how they fly. Let us dive in. To start, imagine you are given a massive collection of vehicles, ranging from tiny, agile drones to massive, heavy cargo planes. You would naturally group them by their engines, wing shapes, and purposes. In the biological world, classifying birds is very similar. Every bird is a highly specialized biological machine, perfectly adapted for its specific environment, diet, and mode of flight. By looking at their feet, which act as landing gear, their beaks, which serve as tools, and their wings for aerodynamics, scientists can group over 10,000 bird species into logical families. Now that we understand the intuition behind grouping birds, let us look at the formal definition. Formally, the classification of Aves is the systematic categorization of birds based on their evolutionary relationships, anatomical features, and genetic makeup. The entire class of Aves is primarily divided into two major subclasses. First, we have Archaeopnetes, which contains ancient, extinct birds like the Archaeopteryx. These fascinating creatures actually had teeth and long, bony tails. Second, we have Neonetes, which includes every single modern bird species alive today. This fundamental split helps us separate the ancient evolutionary pioneers from modern avian life. Building on the subclass Neoornithes, scientists further divide these modern birds into two distinct superorders based on their jaw structure and flight capability. The first is Paleognathae. These are mostly large, flightless birds, like ostriches, that lack a keeled sternum. The sternum is the breastbone, and without a keel, they cannot anchor strong flight muscles. The second superorder is Neognathae, which encompasses all other flying birds. They possess a keeled sternum specifically for flight muscle attachment. From here, the Neognathae are divided into dozens of specific orders, such as perching birds and birds of prey, each defined by highly specific physical traits. You might be wondering, why do we need such a complex system? Understanding the classification of birds is absolutely critical for fields like ecology, conservation biology, and evolutionary science. When we know exactly which order or family a bird belongs to, we can instantly predict its diet, its nesting habits, and its role in the ecosystem. For example, if a new disease affects waterfowl, conservationists immediately know which specific species are at risk. Furthermore, classification helps us trace the evolutionary history of life on Earth, showing us how modern birds evolved directly from theropod dinosaurs. Without this structured system, protecting endangered species would be an impossible task. While anatomy and genetics are foundational, they are not the whole story. Ornithologists also use mathematical biomechanics to classify birds into functional groups based on their flight capabilities. Two of the most important metrics used to categorize bird wings are wing loading and aspect ratio. Wing loading tells us how much weight each unit of wing area must support, which dictates how fast a bird must fly to stay airborne. Aspect ratio describes the shape of the wing, specifically how long and slender it is, determining aerodynamic efficiency. By calculating these values, scientists can mathematically confirm why a swift belongs to a different taxonomic group than an eagle. Let us look closely at the mathematics behind wing loading. Conceptually, this formula calculates the downward force of the bird's weight divided by the area of its wings that generates lift. In the formula, WL represents the wing loading. The variable m is the mass of the bird in kilograms, g is the acceleration due to gravity, and s is the total surface area of the wings. What happens physically when these variables change? When the mass increases without a proportional increase in wing area, the wing loading becomes very high, meaning the bird must fly much faster to avoid falling. Conversely, birds with a large wing area and low mass have low wing loading, allowing them to glide slowly and effortlessly. Before we move on, let us see this formula in action with a concrete example. An ornithologist is studying a wandering albatross. We are given its mass as 10 kilograms and its wing area as 0.6 square meters. We need to calculate its wing loading. We choose the wing loading formula because it reveals the aerodynamic stress on the bird's wings. First, we substitute the mass and gravity to find the bird's weight, which is 98 newtons. Then, we divide this weight by the wing area of 0.6. The final answer is approximately 163.33 newtons per square meter. Physically, this is a highly efficient and manageable load, allowing the albatross to sustain long-duration flight over the oceans. Now that we have calculated the wing loading for a flying bird, let us compare it to an ostrich. We are given a massive mass of 120 kilograms and a relatively small wing area of 1.5 square meters. Using the same formula, we first calculate the weight by multiplying 120 by 9.8, giving a staggering 1,176 newtons. Dividing this by the wing area gives a final wing loading of 784 newtons per square meter. This value is astronomically high. Physically, biological tissues and muscle power simply cannot support this load in the air. This mathematical result perfectly explains why the ostrich is classified as a flightless bird. This brings us to our second crucial biomechanical metric, the aspect ratio. Conceptually, this formula tells us how long and narrow a bird's wings are compared to their overall size. In the formula, AR stands for the aspect ratio, which has no units. The variable B represents the wingspan in meters, and S is the total wing area. What does this mean physically? When the wingspan increases significantly while the area remains relatively small, the aspect ratio becomes very high. This is characteristic of birds that glide over oceans for days. Conversely, if the aspect ratio is low, it means the wings are short and broad, which is perfect for birds that need to make quick, sudden turns in dense forests. Let us apply this new formula to the common swift, a bird known for spending almost its entire life in the air. We're given a wingspan of 0.42 meters and a wing area of 0.018 square meters. We want to find its aspect ratio to understand its aerodynamic classification. We substitute the values into our formula. The first step is to square the wingspan to account for the geometric spread of the wings, giving 0.1764. We then divide this by the physical wing area. The final answer is an aspect ratio of 9.8. Physically, a value near 10 is considered very high, indicating long, narrow, pointed wings that drastically reduce aerodynamic drag. Now that we have calculated these values, let us look at how everything connects visually. On the left side of this diagram, you can see the evolutionary classification tree we discussed earlier. Class Aves branches down into the modern subclass Neonorthes, which then splits into the flightless paleognathy, represented by the ostrich, and the flying neognathy. On the right side, you see a detailed illustration of a bird's wing. The horizontal arrow represents the wingspan, denoted as B, while the shaded region represents the total wing area, denoted as S. This diagram beautifully bridges the gap between biological taxonomy and the physical measurements that dictate a bird's aerodynamic capabilities. We have covered a lot of ground today, so let us summarize the most important ideas. First, the classification of Aves is a beautiful intersection of evolutionary biology, anatomy, and physics. We learned that modern birds are divided into structured superorders based on physical traits like the keeled sternum. Second, we discovered that mathematical concepts like wing loading and aspect ratio allow us to move beyond simple observation. They quantitatively prove why certain birds belong to specific ecological groups. You now have a comprehensive understanding of how every bird is perfectly engineered for its unique place in the natural world. Great job following along with both the biology and the math.